And this is also omega LO. And then you have the other one, because when you multiply by cosine omega LO, half of it got pushed to the right and half of it got pushed to the left. So you also have an image that looks something like that. Okay? So that is M of omega after it has been demodulated once with the local oscillator frequency. It does not go directly to the DC bandwidth. There's no DC term. Okay? And so what happens is that this is picked particularly so that this has a non-zero frequency called the intermediate frequency, omega IF. This is called the minus omega IF. Okay? So, if you do it that way, then now if at this stage, if I design a bandpass filter, I design a bandpass filter called the IF bandpass filter. IF here stands for intermediate frequency. Okay. You will pick up these two bands. If I design a bandpass filter that looks something like this, with HIF omega looks something like that. And it picks up exactly this omega IF signal. Okay, if my bandpass filter is like that, it will pick up that two side bands exactly over there. Okay? And then I work with this signal over here. This signal is not exactly the received signals that I desire, but it is something that has been raised to a higher frequency. Okay? And then if I work with this frequency, I can design low-pass filter or bandpass filter better. Bandpass filters are easier to design than low-pass filters. Okay? So, bandpass filters are easy to design if the if the percentage bandwidth is let me say how I can say this properly. Say if this is having a bandwidth of a certain thing over here. Okay, this has the bandwidth of omega. This thing will be, this actually has a bandwidth of 2 omega, then this will have a bandwidth of 2 omega over here. And then if omega carry is very, very high, okay, then in order to pick up this radio station, you need the percentage bandwidth of 2 omega over omega c. And this could be a very, very small number. A small number, say delta. Okay? But if I push it down to this low frequency, this bandwidth is still about 2 omega, then my bandwidth of my filter is 2 omega divided by omega intermediate. Omega intermediate is much smaller frequency now, so this can be made much, much larger than delta. And yet I will pick up the same signal. Okay? So if I push this into some intermediate frequency, I can pick up this station with a bandpass filter that is more relaxed than the bandpass filter that I need to pick up these different radio stations. Okay? So this filter is easier to design. And then, so let's take an example of AM580. Okay? So what they do there is that they take omega LO to be omega C plus omega IF. Okay, you can see that this is what we have over here too. Omega LO is omega C plus omega IF. Okay, this is omega IF. So if you look at this picture over here that I have, this has been satisfied. okay? Or omega IF is equal to omega LO minus omega C, which means that the omega LO actually has a local oscillator that is higher than that of the carrier. So omega LO is larger than omega C. Okay? So the advantage of doing that is actually twofold. I need to only design this very good filter for only one frequency. This filter has to be high quality so that it can discriminate one station from another one. I only need to design it at omega IF. If I have another radio station that gets a different carrier, push up to a different frequency, okay, I only need to change the local oscillator frequency. I tune my local oscillator frequency for different radio stations that I want to tune to. All of them get down converted into this frequency. And I need to only design this high quality filter for that frequency. Okay? So for different stations, I just turn the knob. Okay? There's a knob somewhere over here. I need to turn. Okay? And then I can pick up different radio frequency, and they all go through this very high quality band pass filter. So I need to design only one filter for all radio stations. Another thing is that if I make omega LO much larger than omega C, it turns out that the range of the omega LO that I need, the dynamic range is smaller in terms of percentage bandwidth. This can only be explained by some numbers, I think. Say if I have a I will quote some numbers from the textbook. Okay. So are there any questions so far as to how this heterodyne thing works? You work with some intermediate frequency. You do the filtering at some intermediate frequency rather than at the low frequency, because it's hard to design filters at the lowest frequency. So, for instance, the textbook says that AM580, the frequency of the carrier is 580 kilohertz. And then the frequency of the intermediate frequency is 455 kilohertz. Okay? And then the local oscillator that you need then is the sum of the two, because the local oscillator frequency is this frequency plus that frequency. Okay, so if you add up the two, then your local oscillator is 1035 kilohertz. Okay? So because you make the local oscillator frequency larger than the carrier frequency, so as the carrier frequency changes, your local oscillator frequency needs to only go over a smaller dynamic range. I don't know if you can see this. Say if the carrier frequency changes, because you make the local oscillator frequency larger, the local oscillator frequency needs to only go over this range, which is a smaller range. Because you can also have the choice of designing the local oscillator frequency so that this thing gets pushed to this one instead of that one. Then you need a smaller local oscillator frequency rather than a higher one. Another way you can get this to work is to have omega LO is equal to omega C minus omega IF. If you pick this, it also works, but this LO is smaller. Okay, which means that you push this to that over there. And then if your LO is smaller, and then as you change your LO frequency to pick up different radio stations, the dynamic range percentage-wise becomes bigger, and it's harder to design that kind of local oscillator. Okay, there's another thing. And there's this issue with an image station too. What happens if there is a station you're trying to push this to IF, okay? This IF frequency is over there. What happens if you have another station that is, say, having a frequency around here? Another station having a frequency around here. And as you push this to the left, this band might go into your IF frequency, and this band might go into your IF frequency. Okay, so there are some interference from other stations that are close by. They can be pushed into your intermediate frequency. Can you see that? Okay, so there's this called image station. Image station is not exactly or immediately next to your radio frequency, but at some frequencies away. It just because you push it in, and because you always have this producing pair, so this thing may get pushed into this bandwidth that you're designing. So if you do that, then your low pass or your intermediate band pass filter will not get rid of interference from this signal over there. So what do? The remedy to this problem is to try to get rid of the station before it gets into your receiver. Okay, get rid of it. But it's quite far away, it's not next to it. So you can design a filter quite cheaply to get rid of it because it's not immediately next to your radio station. To get rid of the radio station immediately next to it, you need a high quality band pass filter. But this image station that is a nuisance is not close to you. So you can design a cheap filter. So the remedy is given in the book. So let me give you the picture in the book. In order to get rid of this kind of image station, interference from them, so you have this RT, and then you have a pre-selected filter. Okay, that will get rid of things like that. You just design a filter to pick up this, and the filter does not have to be high quality. And then you modulate, and then you go through IF, just like we did before, and then you do envelope detection if you want to. Okay, and then you do all kinds of things. So that is a way. This is the local oscillator, omega LO. And this is the way you can get rid of interference from image station. Okay? So these are called super heterodyne receiving systems, and they're quite complicated. So